Okay, so we did this example here. It was kind of more difficult than the previous one, where we had to use the loop law. We did use junction rule, although that junction rule showed us that we didn't really. What the junction rule showed us is that the current stays the same throughout the circuit, right? That's what we see here when we said no junction means same current throughout circuit. Okay, so let's do another one. A little bit harder than the one I just showed you. Okay, so this time I'm gonna add a junction. So let me draw this out. We're gonna have a battery here, and this is gonna go this way. Junction there. I'm gonna have a resistor, and another resistor on this side, and a battery. And that's it. So I'll put some numbers to this. I'll call this one R1. And that's going to be equal to 4 ohms. This one up here is R2. Let's put 2 ohms. And then down here, R3 equals 3 ohms. The batteries, this is going to be a 5-volt battery here. And then on the left side is a 12-volt battery. A little bit better. Okay. So that is our circuit, and we want to do the same thing that we did last time. So with the circuits, let's see here. Okay, so that's really the trick, isn't it? Finding the current through each resistor. Because once you find the current, it's not that hard to find voltage. All you got to do is use Ohm's law, right? V equals IR. So if I get that current, voltage is a piece of cake. But it's getting that current that is going to prove to be difficult. And so this is going to require quite a bit of algebra here. I may skip the algebraic steps just because I don't want to use up time doing the algebra. Anyway, let's set up the circuit. So let's just analyze it and see what we could find out from this. So first of all, when I'm looking at this, there's definitely a junction here. It's 2 junctions. I see a junction here. Oops. Junction here. Okay, so definitely have 2 junctions. I don't know if I'm going to use this, but let me just in case, let me call this junction A and junction B. Okay, I may not use those letters, but at least it's a point of reference for later on. Okay, so that means the current is going to be splitting there. Let's see, and I have a 12-volt battery and a 5-volt battery. Okay, so remember what I said last time, which is not super big deal, but the 12-volt battery is on the left side. That means that current that battery is able to pump out is going to overwhelm the current that the 5-volt battery is able to pump out. So I know my current is going to be going this way. Okay, so like I said, if you didn't know that, just pick a direction. And if you get it wrong, that just means your current, that just means you're gonna get a negative number at the end. Okay, so you could always kind of self-correct as you do your calculations or after you do your calculations. Okay, so I have I going to point A. Then after point A going to the right, I'm gonna call this I1. And going down, I know I should call this I1. And I will call this one over here I2. Because it's going to resistor 2. Okay, so these 2 currents are going through it. They go back to the junction and then come out junction B. and it becomes I again. Okay, and I know because the junction rule, let's focus on junction A, whatever junction goes in equals the junction going out. So I know that I equals I1 plus I2. All right. Okay, so that's what junction rule gives me, and I want to find the current through each resistor. All right, so I'm going to set up a circuit here. Now you could really set up a loop, I should say. I'm going to set up a loop. You could really set up a loop anywhere. You could pick whatever loop you want. I'm going to pick, let me start with the outer loop. Okay, so let me say that over here. So for the outer loop, I'll make that a different color. Okay. So for the outer loop, let's say here's my direction. So you got to pick a direction for your loops. Otherwise, you don't know if you're talking about voltage gains or voltage drops. I'm going to pick the direction of my loop like this. Oops, where's my? Okay, so you can see that direction there. So we're doing a clockwise direction. Let me pick a starting point. I'm going to start here. Okay, so we're going to do what we did last time. We go through the whole loop, right? That outer loop there, and we ask ourselves voltage gain, voltage drops. You know, what do we have going on? Okay, so for the outer loop, as I go around that outer loop, I have. Let me start with that dot. So starting with that dot down here, I'm starting here and I'm going up. So as I start here and go up, we go through this battery, lower potential to higher potential, so the voltage gain there. So we get a voltage gain plus 12 volts. Okay. Keep going around. Nothing here. There's nothing going on. Now you get this junction. Don't worry about the junction right now. We're just following this green loop here. Okay, so I'm gonna keep going, and I get to resistor 2. Well, resistor 2, here's the current, right? The current is going in the same direction as my path here. So I'm going to have a voltage drop through resistor 2. So minus voltage of resistor 2. Okay, let's keep going. Voltage drop across resistor 2, and then we get to that battery. Now, remember the battery, just because it's a battery doesn't mean it's automatically a voltage gain. In this case, we have going from higher voltage to lower voltage, right? So you should recognize that as a voltage drop here, right? If we're going in this direction, going in that clockwise direction, or I should, yeah, clockwise direction, that's a voltage drop for the battery. So I'll put that as -5. I could do that a little bit better. And keep going. 5 volts, nothing here, nothing here. And then we get to resistor 3. Again, that's going in the same direction as how we picked our current. So we're going to take this as a voltage drop here. Okay, so minus voltage of resistor 3. It goes here. Okay, so there's our loop. I could simplify that loop, maybe do a couple substitutions. So, well, I guess I'll do that. So simplifying that, so 12 and then -5 combined, we get 7 volts minus, and then we have VR2, use Ohm's law there. Okay, and then, so that's my Ohm's law. And then VR3, so look at the current going through VR3. The current through VR3 is just I, right? That's what if you look at the circuit diagram right here, we said I is going through R3. So when I write in my equation here, I'm gonna put just I times R3. Okay, and that's as far as I'm gonna go with that for now. We are trying to solve for I. So we want to know I1, and I2, but I'm gonna leave that for now. So if I look at that equation, I have two unknowns in that equation. I guess you could plug in the I1 plus I2 for your I. I may do that. We'll see. Yeah. Okay, so I have two unknowns, one equation. I can't solve for that just by looking at the outer loop. I need to analyze an additional loop here. Okay, so that's what we're going to do next. We're going to analyze another loop here. We got to pick another loop. Let's see. Let's see. I can really pick whatever loop I want. So let's look. I'm going to look at this right loop here. Which way do I want to go, though? Okay, so there's my second loop that I'm looking at. Okay, so we're going to look at that right loop and do the same thing over again. I'll do this a little faster. So for the right loop, get some space here because I'm going to need that. Need that space in a moment. Okay, so for the right, I didn't pick a starting point. Let's have a starting point. Let's have a starting point here. Okay, so that's my starting point right there. So I'm going to start here, and I'm going to work my way around this loop. Okay, and as I'm doing that, again, focus on the direction of the current. As long as we're going in the same direction as current, resistance will always be a voltage drop. You kind of look ahead here. For resistor 1, my loop is going in the opposite direction of current. So we're going to have to deal with that when we get there. It's not a voltage drop anymore. It's a voltage gain. Okay, so we'll get there when we get there. All right, so let's start here. And I go through resistor 1. As I go through resistor 1 here, that's going to be another voltage drop. So let's go back here. So my loop starts off with a negative voltage drop across R2. All right. And then we keep going to the battery, right? We talked about this already, that for this battery, there's another voltage drop because of the direction we're moving. So I'm going to put that as a negative 5 volts. And there's nothing here, so I don't have to worry about this until I get to here. Now, this is what I said earlier. We're going the opposite direction of current. Remember what I said about current? Current always goes from a higher voltage to a lower voltage. So higher voltage here, lower voltage here. But our path is going in that opposite direction. So if our path is going the opposite direction, this resistor here is no longer a voltage drop. If I'm going the opposite direction of current, this resistor is going to be a voltage gain. Okay, so hey, go back here. So I'm going to put a plus VR1 equals 0. Okay, so let me plug in some numbers here. So or use Ohm's law now for the second equation. Negative I2 times R2 minus 5 volts plus, and then the current going through through R1 is I1, so I'm going to plug I1 in here. I1 times R1. Okay, so all I did there was use Ohm's law for my substitution. Oh, yeah, that's minus. Okay, so second equation, again, it can't use that equation on its own. It has two unknowns. So I'll need to combine these two equations. And in order to combine them, they have to have the same variable. So I'm thinking here, probably the best way to do this is to make a substitution for one of them. Let me do this. I think if I substitute, let's go to the top equation here. Going over here, for this I, I'm going to substitute I1 plus I2, right? So I know from my junction rule that this relationship is true, right? For whatever current is going into a junction equals the current coming out of the junction. So I'm going to make this substitution for I. So I guess I could do that. So 7 volts minus I2. Let me plug in my values for R2. So R2 was just 2. Minus, and here's my substitution for I. We're going to substitute I1 plus I2. And R3 was 3. Okay, and we're going to simplify that equation. So I'll rewrite it over here. So what I'm going to do is simplify this outer loop. Simplify this. So that becomes, so get negative 5 I2. What was my I1? Negative 3 I1. Okay. I get negative 3 I1. And then I get a negative 5 I2 equals a negative 7, which I guess I can make these all positives. 3 I1 plus 5 I2 equals 7. Okay. Oops. All right. So that is my simplified equation for the outer loop in terms of I1 and I2. And then for the right loop, I'll put that down here as well. Okay, so for the right loop, it's not, that one doesn't require that much simplification. So we get, let's see, and plug in my R1s. So R1 is just 4, it's 4. So 4 I1 minus 2 I2 equals 5. All right, so does VR3 not have an I with subscript like VR2 because of junctions? Yes. So VR3, go over here. Yeah, here's my R3. R3, by the time current got back to it, it had already combined. Here's my I1, here's my I2. So the junction, yeah, combined the I, or combined these two currents, and this gives us back the I that we started with. Yeah. So that, because of that junction, the VR3 does not have a subscript. And when it has, this is the subscript I'm talking about. Or the I without subscript is related to the ones that do have subscripts. All right, will we have been able to create a loop on the left side instead? Yeah, yeah. So the kind of nice thing about this loop loss is that you could set up your loops whichever way you want. You would have to set up 2 loops. because you can't solve this with just one loop. You need to set up at least 2 loops so that you could form your system of equations like I have here. And once you form your system of equations, then you do all the algebra to solve for I1 and I2. Yeah, but we totally could have used the left side instead. Okay, so there's our equations. We can now solve for those system of equations. You can use matrices if you know how to do that. You could use the substitution method. I prefer for this one, it's simple enough to use the elimination method. Right, remember your algebra. But like I said, I want to save some time here. So I'm not going to work out at least all the details here. Okay, so what I'm going to do here is I want these to cancel. So let's see. Okay, so I can multiply the top by 2 and the bottom by 7. Oh no, top by 2 and bottom. So I'm going to multiply this times 2 and this one times 5. What that will do is eliminate my I2. I guess I will work it out. Okay, so I'm going to put a line here so that okay, so if I do that, I get these equations. 6I1 plus 10I2 equals 14. And the bottom, 20I1 minus 10I2 equals 25. Okay. This is 14 here. Okay, so I'm just doing my system equations here. Oh, can you explain how you have a positive VR1 in the right loop? Yes. Yeah, so that's tricky. It's definitely worth going back. So right here, you need to know 2 things to explain that: the direction of current and the direction of your loop. For your loop here, the loop that I made, is clockwise, right? So at this point, at resistor 1, my loop is going up. However, we said the current was going down. So the reason why it's going to be a voltage gain is because, remember, current always goes from a higher voltage to a lower voltage. So that means over here on top of the resistor, I have a higher voltage than I do down here. It's going to be a lower voltage. So if my loop is going like this, it's going from a lower voltage down here up to a higher voltage here. So that would be a voltage gain. Okay, so summarizing that, anytime your loop goes in the opposite direction of your current, you're going to have a voltage gain for your resistor. Okay. All right, so let's get these numbers. So yeah, so you get 26I1 equals, what would that be, 39 volts. Okay, so then I1, 39 divided by 26. I don't have my calculator. 39 divided by 26. Oh, 1.5, thank you. All right, 1.5 amps. Okay, so I have my I1. That's the current going through my first resistor. And now we just plug it back into one of those equations, the equation for the outer loop or for the right loop. Doesn't really matter which one. But if you do that, you get I2 equals to 0.50 amps. Squeeze that in there. I'm pretty sure you do. At least that's what I have written in my notes, so hopefully I'm correct. Double check that, though. I have made mistakes. Okay, so having I1, having I2, now of course you know, we could get I, right, using what we got initially here. Right over here, right? I1 equals I1 or I equals I1 plus I2. I know my I1, 1.5. I know my I2, 0.5. So then my I, right, my total current going through resistor 3. I know why it stops working sometimes. 2.0. Okay, so we get our currents. All right, so it took a lot of work, particularly setting up those loops, right? If you mess up with those loops, things could fall apart pretty quickly. So be careful when you set up your loops there when you're doing these kinds of problems. All right, let me pause here. As far as summarizing goes, yeah, it's just like I said, you can set up any loop you want. Oh, one thing I wanted to say here, if you look at the currents, all the currents are positive, indicating that the directions I have written on the diagram there are correct. Okay, so the currents are indeed going in the direction shown. If one of those were negative or any of those were negative, it would tell us the current is actually flipped, going in the opposite direction, which that does happen from time to time. Sometimes, depending on the circuit, it's kind of hard to see what direction the current's going initially.